Thanks for coming. My name is Juan Cañada. I'm a lead programmer at Epic Games. And well, today we're going to talk about how we implemented ray tracing on Unreal Engine 4.22. We'll also show how we made the movie Troll, how we helped Goodbye Kansas to make the movie. We'll talk about the challenges we face, how we approach them. Then Goodbye Kansas will give a breakdown on the art and content, on the workflow of the movie. And finally, Patrick Kelly will explain in more in depth how the implementation of ray tracing is in 4.22. So let me first summarize what we have done this year. Surely you remember that a year ago we presented the movie Reflections in collaboration with ILMX Labs and NVIDIA. And well, that was great, that was beautiful, but that was just the beginning. It was obviously not the place where we wanted to be at the end. A few months later, also in collaboration with NVIDIA, we presented the movie The Speed of Light, which shows more sophisticated ray tracing effects. And with all the lessons learned during this year, we have rewritten the whole ray tracing technology. So it's not a prototype for demos anymore, but this is something that is actually part of the Unreal Engine code base. And we partnered with Goodbye Kansas for making a movie called Troll. And we are going to watch it now. So the goal of Troll was not to showcase ray tracing because we already did that last year, and we don't want to repeat ourselves. The goal was to explore how far we could go in terms of real-time digital content creation and how we can mix ray tracing effects with other sophisticated tools of our cinematographic pipeline, like the sequencer, Alembic, the geometry cache, Niagara particles, and of course, digital humans. All these components have been greatly improved because of this demo, and now they are part of 4.22. The second goal was to make this demo with code that is accessible for everyone. The previous two demos, Reflections and The Speed of Light, they were done with private code by Epic people, internal technology. This time, this code is the same that you can use in 4.22. That will be released next week, but has already been in GitHub for a while now. Let me show you some numbers on the demo. Well, basically, this demo is one order of magnitude more complex than the previous ones. There's more polygons, there's more lights, the environment is way more complex. The quality is higher because we are rendering ray tracing passes at full resolution instead of a half resolution like last year. There's many other elements, as I already mentioned, Niagara particles, digital humans, Alembic, geometry cache, and so on. But the render time is the same. So the render time is the same, the complexity is much higher, which means that performance is way, way better. performance is more or less 1 order of magnitude higher than a year ago. I have not talked about hardware yet. This is the hardware we use for reflections. A year ago, this is a high-end DGX station with 4 NVIDIA Teslas. This is a high-end machine, not very cheap. And this is the one we have used now. This is just one single 2080 Ti, just one GPU, and it's a consumer-grade GPU. When I say that this demo is more accessible for everyone, I am not just talking about code that you all can use, but cost is critical for accessibility. And from the very beginning, we said we have to do a demo that runs on a single GPU that most of our Unreal users can buy. There were many technical challenges, as you can imagine, on this demo. I'll just focus on these 2, mostly on performance. Performance was, unsurprisingly, the most challenging thing of the demo. I will have a separate talk or an entire day just for talking about performance, but I'll just show you some bits. This is the performance chart 2 months ago, when the contents were more or less ready, and we started to work on optimizations. The dotted line is our budget, which means that we were not in a good place. Most of the frames were taking like 60 milliseconds, 80 milliseconds, some of them even 100 milliseconds. So what did we do? Well, we did a lot of things. Actually, not all of these things were related to ray tracing. The first one, it's a shift from immediate to retain mode. The ray tracing technology has been built on top of a major refactoring of the rendering pipeline that happened this year. Marcus Wasner has just given a talk about this refactoring. This refactoring has lots of things, but one of the key factors of such a work was that we have shift from immediate to retain mode, which at very high level means that we are not recomputing everything at each frame all the time, but we are just recomputing things that have actually changed. That's very important for ray tracing because of the nature of ray tracing, a ray can travel everywhere in the scene. So you need to get access to the whole geometry and all the materials, and we don't have the budget to recompute that at every frame. We need to shift to a retain mode where only things that have actually changed are recompute. And that made it possible to build a much more efficient ray tracing implementation on top of this refactoring. There are many optimizations regarding ray tracing specifically. I will just focus on a couple of them, the ones that we consider that are more important. Interestingly, shadows and ambient occlusion are very fast, surprisingly fast. Artists were shocked to see that they were, and sometimes even faster than raster shadows, which makes sense depending on the scene, because we don't have to recompute shadow maps, and well, the code path is very different. So we expect that people start using shadows and ambient occlusion with ray tracing now. Of course, there are other effects, like reflections or translucency or global illumination, that are not that cheap at all. And we need to apply different strategies for being able to render them and produce these kind of movies. Of course, denoisers are always critical, even for shadows and AO. I said they were fast enough, but they were fast enough with denoisers. Our rate budget is very low. We can just trace a few rays per pixel, so denoisers are critical. So what do we do for improving ray navigation? Well, you have 2 main rules that we follow. The first one is that we trace rays only when they are really needed. And the second rule is that we trace rays as short as possible. The fundamental idea of tracing rays only when they are really needed is that when roughness is very high, well, when roughness is high enough, ray divergence is also high, so you really cannot see accurate reflections, and you can fall back to cheaper mechanism. So for instance, in this image, maybe you need ray tracing reflections for simulating with accuracy reflections in water ripples, but you don't need ray tracing reflections on the rocks. They are very lossy, the roughness is higher, and you can just use other strategies for that. You can save a lot of time with this kind of roughness cut and similar tricks. There is a second strategy that is very effective that I just mentioned, which is like tracing rays as short as possible. For instance, in this scene, if you are computing ambient occlusion on the face of the Princess Bianca, you don't need to trace like super long rays that travel around all the scene and have to do a lot of intersection tests with trees and so on. You can lose some accuracy. It's not unbiased, it's not super accurate, but it's very effective and really works great for real time. Niagara particles were another big challenge, not specifically just related to ray tracing, but having a lot of particles running in real time, it's something hard to achieve. We had more or less 650,000 particles, and they were moving quite fast. That means that we cannot use an acceleration structure for ray tracing that we just update at every frame, because the movement is very dramatic, and that acceleration structure, that BBH, will degrade quickly. So we have to reconstruct the BBH at every frame. That is very expensive. So what we did was very simple, but was very effective. We have, as I said, almost 700,000 particles on primary visibility on the raster side, and we feed the ray tracing with only a fraction of them, 1/3 of them. And we compensate that increasing the brightness. It's simple, but it works. Of course, that means that Niagara particles are visible in ray tracing effects like reflections. And after applying all those strategies, we move from this chart that I showed you a few slides ago to this one. This is where we are now. We were yesterday, actually, we generated this chart. We are on time. And actually, there's room for artists to push the limits even harder. But we didn't tell them. Yeah, it's always a problem, right? And then, the other big challenge was digital humans. Achieving very realistic digital humans is hard. Now it's not that hard. With Trilateral being part of the Epic family, everything is getting easier. Talking about digital humans it's a separate topic, not for this talk. I'll just mention that ray tracing makes easier to achieve a realistic looking when rendering digital humans because, well, you can use rect area lights, you can play with soft shadows, and you can achieve realistic looks with less effort. For the Troll movie, we implemented barn door lights, like the one you see on that picture, and they are part of 422 now. Barn doors are a standard on real cinematography. So it's great that now we have them in the engine, and they are part of 422. That's another good example of how these movies and these demos help Unreal Engine to be better. And that's all from my side. I will hand the presentation over to Anton Palmquist, head of real-time at Goodbye Kansas. He will tell you how they made the movie, and we'll do a breakdown on workflow and art and content. Thank you.
All right. Thanks, Juan. I'm Anton. I'm head of real-time at Goodbye Kansas Studios. So Goodbye Kansas is a visual effects studio where we work on game trailers, cinematics, feature films, TV shows, and advertising. We have our headquarters in Stockholm, in Sweden, in the middle of the game dev hub of Södermalm, and we've been fortunate enough to work with many different game studios throughout the years. So games are in our DNA, so we have our feet in both camps, so to say. So it's only natural that we've been looking into game engines, and it's been the plan all along to explore what we can do in real time. So we also have an office in LA that's specially focused on real-time projects as well. We've been working on integrating Unreal into our VFX pipeline for the last 2 years, and we're using it for previs, but also final render, like this Troll project. Game studios that are using Unreal are especially interesting to us because then we can work on the same Perforce server. We can set cameras, do the lighting, use game assets directly from the game, and that saves us a lot of time in look dev and asset build. So we've been waiting for a long time for this, and finally we have ray tracing in a game engine. So now we can use lighting concepts that we're used to from offline rendering and real-world cinematography. We now get correct reflections, which is a big improvement to SSR and planar reflections. We have translucency, where we get much better glass and liquid, which has been really hard to achieve in real time before. Area lights gives us a much more natural look with soft shadows, and that's really crucial when lighting a digital human. Real-time GI means that we don't have to rely on light bakes anymore, so we can get realistic bounce lighting without having to wait for the bakes. All in all, we have a much more cinematic way of lighting, so let me show you how we use this in Troll. So here you can see the reflections in the water. We don't have those nasty SSR artifacts anymore. You can see here the area light lighting up Bianca's face, and we go from hard to soft shadows. And here in the crown, you can actually see the fairies being reflected, and you can even see her face in there. And we also have ray traced translucency now, so we get physically correct absorption and refractions like in the water here. So to help our artists use tools that they're used to, we created some of our own in Unreal. So with the material editor and blueprints, we can quickly customize the engine, so we can introduce classic visual effects pipeline workflows. So with this, we're lowering the bar of entry for artists that are new to a game engine while maintaining the strict quality control that we need for visual effects. We also have Python support, so we can extend our pipeline just like we do with other applications that we use. So here, for example, we created an Uber shader, so the artists don't have to create their own shaders, saving lots of time and troubleshooting. We also implemented UDIM support, so we can use our assets directly from our pipeline. And this is just a material function, so it's nothing fancy here. It's made in the node-based material editor. We also made this light rig to have a quick look dev environment for the artists. And now with ray tracing, we get an even more accurate one-to-one match from what we expect from an offline renderer. It also has runtime control, so we can pack it up, and we can use it for dailies or even send it off to a client if they want to review the assets interactively. We also got some good improvements to Alembic in 4.22, which made it much more efficient. And for this project, the dress was simulated in Houdini, and then we imported it as Alembics for each shot. And Alembics is just a huge thing for us, and it's nice that it's working so well now in Unreal, because as a VFX studio, we're using Alembics for everything. So all in all, we have a really robust tool set now for creating cinematics in real time, and it's a whole new way of creating content for us, much, much quicker. With that also comes a change of thinking about production planning, where more things happen in parallel, just at the same time. And we can do lighting decisions very early on, and we can do final tweaks until the very end. So it's a big change from the linear thinking that we're used to in visual effects. So that's it for me. And with that, I'd like to introduce Patrick Kelly, senior rendering programmer, and he will go more into depth on how we made this possible. Thank you.
Thanks, Anton. As he said, I'll be breaking down some of the more technical components of our ray tracing implementation that's going into this 4.22 release. Here's the outline for my section. I'll be starting off talking about the underlying RHI layer, sort of the nuts and bolts of what gets us down into D3D12 and the DXR implementation. We'll bubble up after that. I'll talk about the mesh pipeline, how we get the geometry and shader binding information down to the D3D12 layer, and the general execution flow and the path structure. And then I'll finally finish out the talk talking about the render passes that put the pixels on screen. Right, so for the technical outline, we'll go ahead and jump right into the 4 main constructs of what we have at the thin RHI layer. Here's a small amount of pseudocode generated in our engine to just kind of give you an insight into the creation mechanisms for what we have. So at the top level, we have ray tracing geometry and the ray tracing scene. A scene is composed of multiple ray tracing geometries, but typically we only have one scene at a given time. Each of these geometry shaders, or each of these geometry components are tied together with multiple types of ray tracing shaders, closest hit and any hit shaders. But we also have different new DXR types, right, like the mist shader and the ray generation shader. Those aren't tied directly to geometry, but rather to the ray tracing pipeline state, which is the last component and the overall encompassing structure that binds everything together. As far as the ray tracing geometry is concerned, it really is a bunch of triangles. So it's a bunch of position vertex information and index spans. We have a bit of a nuance in UE4. We have this concept known as ray tracing geometry segments, or just geometry segments, which are spans of the index buffer bound at the geometry. And the nuance behind this is that we can embed different material information associated with these index spans. So they're governed by a large overarching geometry, but can point to disparate types of materials. Another common thing that I don't have in the initial slides, but is incredibly useful, is the ray tracing geometry instance. This binds transformed data directly to the geometry that we have in the scene. It's a bit of a memory compaction for things like static meshes. This can be a huge win. For other things, it's just a nice encapsulation layer. The other 2 components that are worth mentioning is the user data and the mask. The user data we use as an index to do lookups in our closest hit shaders so that we can recall specific primitive lookup data. So if we want to fetch textures, fetch other sorts of vertex data, that's what we have at our disposal. And lastly, the ray mask, or the geometry mask associated with the ray mask, and allows us to do things like hide certain geometries from certain passes. We can fire rays and only hit Niagara particles, things like that. Moving on, the RHI scene is just a collection of geometry instances. It's pretty bare bones. There's not a lot more to say except that it encompasses all the geo. The RHI shaders are brand new. They mimic directly the DXR shaders that we have in D3D12. So to sort of break those down, we have closest hit and any hit shaders. We have mist shaders and ray generation shaders. For those of you that are familiar with DXR, you know that we are omitting from our list here the intersection shaders and the callable shaders. We technically have support for intersection shaders, but they're not plumbed all the way through the pipeline. And we currently do not have support for callable shaders, but we intend to provide those very soon in a future release. So to kind of bundle up a few of these shader types, we have closest hit and any hit that we associate with a particular geometry. And we have mist and ray generation shaders that are typically associated with a pass, but they exist in a sort of decoupled state in that realm, but are bound together in the ray tracing pipeline. The ray tracing pipeline is a term that we use that's analogous to the compute and graphics pipeline state objects that we currently use. A difference is that we have only one ray tracing pipeline state object for all shaders. We do this as an optimization, so we're not switching out different types of pipelines for particular passes. So instead of that, the ray tracing pipeline state object holds all of the shaders that we might ever use for a given frame. One particular small note is that we have a trivial mist shader. Some people you've seen have some fairly complicated mesh shaders. We just basically tell the ray generation shader we've missed, and you handle it. That's typically how we operate. One thing that we are missing from the highest level is the idea of the shader binding table. And our decision here at the RHI layer was to encapsulate that away from the user. So instead, we use this function set ray tracing hit group, and that is responsible for taking the any hit and the any hit and the closest hit shaders and binding them directly into the SBT. And this is done without the user really knowing the nuts and bolts of what's going on in the SBT and taking away the SBT management. We haven't completely decided whether this is the best thing to do, but for now, this is how we're going to operate. I'm going to go ahead and move on to the mesh pipeline. I'll talk about the different geometry types that we support, ways that we can extend support in the future, and some special considerations about how we're currently doing things and how we might change. So for the mesh pipeline, we have two main stages that happen at the beginning. The first thing is to gather up all of the ray tracing geometry instances. We have statically cached instances that are coming from previous frame data, and we have dynamic instances that are being injected live into the render. We have a virtual function that's used to get dynamic instance data, and that's the thing that I'll talk about in a moment that developers can use to extend for custom geometric primitives. After that, we have our ability to dispatch ray tracing updates. And so this is fairly straightforward. This basically means we're about to rebuild the acceleration structures. What things do we need to do to prime those so that they're ready? So typically, things like updating vertex positional data, actually updating the bottom level acceleration structures, which are encompassed by the ray tracing geometry. And then after all that is done, to rebuild the entire top-level ray tracing scene. The final two sections are just sort of the nuts and bolts of the rest of the pipeline that we need to operate. So because ray tracing render passes operate on the G-buffer, the base pass needs to be executed. And once that's done, we pretty much have free reign to trace any ray that we want. To talk about supported geometry, we currently have static meshes, skeletal meshes, geometry cache, which is our Alembic support used in the demo you saw earlier, and Niagara particles. There are a number of geometry that's missing. Things like landscape and foliage come most often to mind in people's minds on the forums as they post. And we intend to support this very, very soon in the near future. That's actively what we're working on right now. In terms of extending geometry, if you have your own geometric data that you want to embed into ray tracing, we have a function for you. It's called Get Dynamic Ray Tracing Instances. It has a few things that are on its onus to implement. So for the first thing, it needs to implement or recall a ray tracing geometry. It needs to bind transformational data to construct the instance. So as dictated sort of by the name of the function itself. The last thing it needs to do is to decide how to bind material data for each geometry segment. And rather than because this is a bit custom in all of our implementations, static mesh is very different. It doesn't even use this method, but all of the other geometries I spoke about use this method. We just referred you to look at Niagara renderer sprites as a concrete implementation of how you might go about extending something like this. In terms of special considerations for what to do with different geometries, there are a few options. The first thing is whether or not you decide you should rebuild your acceleration structure from scratch every frame, or if you should refit it. We did a little bit of experimentation here, and we found that in all of our needs, rebuilding the acceleration structures were the best thing. So that's pretty much what we did. For level of detail, our level of detail support only exists within static meshes. It doesn't exist for any dynamic geometry. The Get Dynamic Ray Tracing Instances method is meant to provide the instance to be used into the scene, so the level of detail support could be handled there if we so choose. But really, it's only available at the point of generating the static meshes. The last thing is visibility, and by visibility, I mean like actual inclusion into the ray tracing acceleration structure itself. So the choices that most come to mind for artists is that they want to hide something from being a shadowing occluder, and so we have this special type here to provide them with this faculty. All right, finally, I'll be talking about the render passes that we've used in our demo, and also some experimental integrators that we're messing around with and might provide some inspiration for how you might go about extending it yourself. So the most obvious thing, and probably the most easily drop and replace solution that we get with 422 and ray tracing is the ability to do ray trace shadows. It was a pretty simple drop-in solution and replacement for traditional shadow mapping, so that made it really nice. We support ray trace shadows for directional lights, point lights, spotlights, and rect lights. And all that's nice, but one of the big compelling features of ray trace shadows is the ability to create shadow visibility masks from area sources. And so we have that. This is an image here using a number of rectangular area lights. So in terms of area sources in 422, we have support for rectangular area lights, spherical area lights, and directional disk lights. So you can have sort of soft sun shadows in this manner. So sort of technical detail, we generate all of our shadow visibility masks with 1 sample per pixel. So as you can see here on the screen, it requires quite a bit of denoising to reconstruct the result. So this is a raw input from a directional source, and here's the denoiser result. Just for clarification, this is a result not denoised using 64 samples per pixel as a reference. So you can see that the denoiser is doing a pretty good job here. I'll move on now and talk a bit about ambient occlusion. Ambient occlusion operates in a similar manner to ray trace shadows, where it is simply also a drop-in replacement. This time it's replacing screen space ambient occlusion. In order to generate this pass, we're doing pretty much a traditional thing that you would expect. We're sending cosine weighted rays out into the hemisphere, and it's recording the hit and miss ratio and returning the result in terms of a visibility mask. Of course, the main usage of ray traced ambient occlusion instead of screen space ambient occlusion is that it can fire not just against the G buffer, but against the scene. And so in this example here, you can see that screen space ambient occlusion is having a hard time resolving the AO that's under the furniture, whereas ray traced ambient occlusion picks it up. Of course, ray traced ambient occlusion is quite noisy, so we need to denoise the result, and this is what we get. Before I continue with the rest of the render passes, I should note that the previous 2 are visibility render passes, and the next 2 are material render passes. And requiring material support and the closest hit shader incurs a bit of cost. So we do find that when using visibility rays, we prefer this approach as to actually having to implement and execute closest hit. In order to grab access to closest hit shaders and give material data, we bind, at the earlier function I mentioned to record shader binding table instructions, we bind vertex interpolant information and material graph execution. That gets bound together through our compiler and turns into a closest hit shader. Okay, moving on, talking about reflection. Reflection is somewhat similar to the AO pass I described, where we start from the G buffer and we distribute some number of rays. Instead of firing rays in accordance to some cosine hemispherical distribution, we fire rays in accordance to the GGX distribution. Upon hitting a secondary light source, we perform a light loop integrator and return the result to the screen. One of the caveats or just special considerations about reflections that make them hard is that if you don't do the exact lighting calculation for the secondary bounce, you're going to get something in reflections that doesn't mimic what happened in the base pass. So we have to do special care to sort that out. And it doesn't necessarily play well with some of the other integrators that I'll introduce later. Ray tracing allows us to overcome some artifacts that you would see, as shown here with screen space reflection. Since we can only reflect things on the G buffer, we miss some prominent occlusion and detail that are in the scene that we don't have otherwise. So this is the SSR version, and this is the RTR version. One of the other things that we can do with ray traced reflections is the ability to cast multiple inner reflections. In this example, just as an example, we cranked up the number of maximum ray bounces to something like 5 to get a ton of inner reflection. You can see here, this isn't a real-time result at this point. We're showing a pretty picture, but it's just to exemplify things that we can do. Typically, we limit the number of reflection bounces to 1 or 2 so that we can have it be runtime performant. And now I'll talk a bit about the translucency pass that we use. The translucency pass is a bit different from the reflections pass. The idea being that we need to trace from the camera to the G buffer and intersect against some transparent surface that was in between. In this manner, we say we've done this and we found that that transparent surface. Now we're gonna execute a reflection or refraction pass that is almost identical to the reflection pass I just described. So again, we hit the secondary surface, we cast a reflection and a refraction ray optionally, and then perform direct lighting on the result. If we can do this well, we can model something like transparent glass. One thing to point out is that actual structures with indices of refraction causes a lot of computation. So we do prefer, if we can at all costs, trace a refraction ray through a material with complete transparency, or with the index of refraction equal to 1. All right, finally, to round off my section, I'll talk about some experimental integrators that we've been messing around with. And before I introduce them, I want to talk a bit about some of the methodology behind the sampling that makes these things work. So for these experimental integrators, we use a thing called hierarchical sample warping. This is introduced by Claerberg et al. In 2005 in their paper titled Wavelet Importance Sampling, Efficiency Evaluating Products of Complex Functions. In this paper, the authors describe a way to basically permute a uniform random distribution sequence, or any random sequence that you prefer, and push it through this importance sampling map, this importance sampling structure, to generate sample points that are warped by this new distribution. And I refer you to a Ray Tracing Gems article that just came out. It's chapter 16 called Sampling Transformation Zoo. It has a really good breakdown of the query structure embedded in doing this. But basically, we construct some decision tree decided by probabilities of choice, and the descent through the tree warps a random variable that we pluck from our random function through this distribution to arrive at a function that we deem worthy. It's really great for doing things like textured sampling. And so this is exactly what we do for textured area source. And if we can do this with a rec light, we'll get something different than the traditional rec light shadow integrator. We can get colored shadows in this manner, and they'll be importance sampled directly to the area on the texture where the irradiance is highest. One of the other things we can do is we can embed the same sampling structure in terms of sampling a skylight. And in this instance, the skylight has the directional lighting term baked into it, so there is no external sun. It's just embedded inside the sky dome. This allows us to get sharp shadows from a directional source as though it was existing, but instead we're just using this nice text cube instead. Obviously, this is only the direct lighting result. We need something else. For that, we have the experimental GI integrator. The experimental GI integrator operates in a similar manner to the ambient occlusion pass that I mentioned earlier, with the exception that instead of performing visibility, it evaluates material hit information. Unlike the light irradiance loops that happen in the reflection and translucency pass, this shader is actually using next-event estimation, which does a stochastic light selection. It's much more akin to path tracing than it is, say, for the stochastic ray tracing that I introduced earlier. And finally, we had a bit of time here before GDC, and we wanted to put together a bit of an experiment in image-based lighting. And the whole point of image-based lighting, it's a staple in visual effects, but the idea is to go on set to record something, with the actors and in the environment, and to place a capture device so that you can actually record the lighting that was shot on set at that time. That Skydome is taken back to the CG studio, where artists redevelop the scene in CG, and then they reproject the captured lighting back onto the set. It's a very particularly powerful lighting technique that's used in that field. And for that, we wanted to use this nice demo scene that you saw earlier in a keynote from Quixel. This is a doctored lighting example, but this is an example that is running basically right now today in 421. This is using traditional rasterized cascade shadows. It's using the spherical harmonics integration of the skylight, and it's a pretty nice result. And what we, of course, experimented with doing is by providing the skylight integrator instead of a directional term and instead of the SH version. And so this is what we have. As another aside, we are employing ray-traced ambient occlusion here instead of screen space ambient occlusion. You can see that it's quite a bit darker. I'll flip back and forth. So this is really just the direct lighting term. So we're missing something, and so for that, we're going to throw in the GI term. And so this is the skylight integrator with the GI term. The window panes you can see are a bit different. It's because I have a bug in the screen space or the ray trace reflections that I get to sort out after this talk. And this is the example running with a much higher samples per pixel count at 1 frame per second. So not real time, but it's not too far off. So this, just to go through some stats, the 24 frame per second example is running with 16 samples per pixel of the skylight and also 10 samples per pixel for global illumination, whereas the 1 frame per second is using 128 samples per pixel, not really feasible, but still delivers a nice result, and 10 samples per pixel for GI. The other thing to mention is that there is no denoiser right now being applied onto the skylight, so we do anticipate that we're going to be able to bring this number dramatically higher in the future. Lastly, one of the other main sort of touting bits of ray tracing is the ability to do dynamic lighting. So we took this set and we took the skylight and we decided we would do a time lapse instead. So this is the 128 sample per pixel high fidelity image that I showed before running through an animated time lapse. You can see the time lapse in the bottom. It's a bit long time lapse. I had to wait for it to finish. I wanted to thank Joji and Marian for putting this shot together and testing sort of the stressors of what we could do with image-based lighting. As a final note, 422 also ships with a path tracer. I wanted to give a little bit of information about what to expect from this thing. So this is not currently a device for generating final pixels. It's a device for generating reference imagery that engineers and shader writers can use to validate their results, their experimental real-time results, against a ground truth reference. It's meant to be an unbiased representation. We're not cutting any corners right now with how that path tracing integrator works. So it's noisy, it converges, it takes a long time. But it's meant to be used as the foundation for other types of render passes that we could use to accelerate in real time. For instance, I already brought up the ray tracing global illumination pass, which is based on the path tracing integrator, and we anticipate that a similar interactive light baking integrator might also be using this model in the near future. All right, that's it for me. I'm going to hand it back to Juan to close out. Thanks.
Thanks, Patrick. Thank you. Yep. Just a couple of things before we finish. I would like to talk a bit about the future. What is next? Ray tracing has been released as an early access technology, which means that our goal now is to make it more stable and to make it more efficient. That's our first thing we are going to do. Keep working on making this production ready. Of course, we are going to improve the noises, the path tracer, and well, many other things that are not totally supported now. For instance, we don't support all the geometry types we support in the raster path yet. We will make use of the intersection shader for supporting landscape, for supporting volumes and other geometry types that are not entirely supported, as I say. We will work on multi-GPU support, too. And we are also working on an interactive GPU baking tool. And many other things that you will see on time. I cannot finish my talk without saying thanks to the heroes, render engineers that have been working on this project. That was amazing. I will remember that forever. There's many other people who I should say thanks. There's no time for that. I will need a lot of slides, and that doesn't work. So just final takeaway is that ray tracing is ready, unfortunately, too. You can already use that. It's still early access, but it contains a complete set of features for creating high-quality pixels, and we can wait to see what you do with that. Thanks a lot for coming, and I hope you like the talk. Do we have time for questions? Yep. We have time for questions, and probably we have microphones somewhere. Yep.
Can't tell where questions will be coming from.
Sorry?
So I don't know where the mics are at.
No questions. Easy. Yeah, no.
Yeah, you got it.
Hey,
stage mic this time.
Okay, I think it's on.
Excellent.
Hey, in terms of loading Olympic files, is there like a simple formula on how much data you can pull into Unreal now? So if you have a certain amount of meshes over your geo, is there a ceiling that you can hit
So
where you
for
start seeing a major performance hit?
Yeah, we haven't really stress tested that, but for this project, we had geos for almost every shot that were loaded at once, and each geo is between 500 megs to 1 gig, and they were running very smoothly.
Like the main character, her outfit and her body, what were the numbers, the polygons?
So the dress is around 100K triangles. Yeah.
On the, sorry.
No?
On the landscape that Patrick showed, we don't have dynamic unscalable meshes there, but we have done some renders with 450 million triangles. They are static meshes, so that means that you can put a lot of geometry in the GPU, but we really don't know the limits. We have not explored how much Alembic you can fit in. We don't know the ceiling, basically. We had enough for this movie, and we didn't explore beyond.
And the fairies, was that geo, or was that just point cloud?
So it's both. So it's a geo. For each of the fairies, it's 10,000 triangle geo, just to get that outline effect, and then we have particles emitting from them. And I think the total particle count was around 2 million, something like that.
And I guess the volumetric smoke, is that native in Unreal? Is that like a secondary plugin, or?
You mean the fog on top of the lake?
Yeah, the fog that's coming off of them for the particles.
Yeah,
is there anything added that you had to have a different plugin, or is it all going to be native in 4.2?
It's all Niagara. Yeah.
No more questions? Well, Thanks again for coming. I hope you enjoyed the talk.
Thank you.